Welcome to Propeller Breeze, the show for student pilots, sim fans, and everyone chasing that first solo and beyond. All information in this podcast is for entertainment and general knowledge only. Always verify with certified flight instructors or regulatory authorities before attempting anything mentioned here.
Picture this scenario. You are on short final.
Oh, yeah.
The runway is looming up in the windshield, the numbers are getting bigger, but you realize you're a little low.
Right.
Your hand instinctively pulls back on the yoke to fix the picture. But instead of floating up nicely to the glide path, the sink rate actually increases.
Yep.
The stall warning horn gives a little chirp. Your instructor, sitting right next to you, suddenly barks, "Power! Power!"
It's a scenario almost every student pilot has faced. It's that moment of sheer panic where your hands do what feels totally natural, but the airplane does something completely different.
Exactly. And usually that's the exact moment you realize that your intuitive understanding of how an airplane flies might be, slightly incomplete.
Or just flat out wrong.
Right. I mean, it brings up that eternal cockpit debate that never really seems to die.
The old pitch and power debate.
Yeah. Pitch for airspeed, power for altitude versus pitch for altitude, power for airspeed. I've had instructors who would practically wrestle you for the controls if you used their wrong method.
It is the classic flight training dilemma. And honestly, both of those rules of thumb they're just that. They're rules of thumb.
Right.
They work in very specific situations, but they completely fall apart when things get dynamic. They obscure what is actually happening with the physics of the machine.
Which is exactly why we're here today. We are doing a deep dive into a really fascinating technical analysis titled The Energy-Centered Approach to Aircraft Flight Control.
That's a great paper.
It really is.
Yeah.
And I have to say, reading through this source material, it felt like someone finally turned on the lights in a dark room. It stops being about memorizing inputs and starts being about truly understanding the machine.
It's a total paradigm shift.
Yeah.
It moves us away from memorizing those if this, do that inputs and toward understanding the airplane as a complete interconnected energy system.
So if you're a student pilot working on your PPL right now, buckle up. We're going to talk about energy today.
And we don't mean the caffeine buzz you need for a 6 a.m. flight block.
No, definitely not. We're talking about the mechanical energy of the aircraft. The mission of our deep dive today is to stop you from chasing needles on the six-pack and start managing the airplane's energy state.
Precisely. Because once you understand the energy state, you stop guessing. You really stop fighting the airplane. You start managing the resources you actually have available.
Let's get right into the cockpit then. We have the throttle and the elevator. Most students are taught, I was taught throttle makes you go fast, elevator makes you go up, or, some variation of that.
Depending on who taught you, yeah.
Right. But this analysis says we need to completely relabel these controls in our heads.
We absolutely do. But before we stick new labels on the dashboard, we have to define what we mean by energy state. It sounds like a bit of a buzzword, but in physics, it is very specific.
Okay, lay it on us.
An airplane's energy state is defined by the total amount of energy it possesses and, crucially, how that energy is distributed.
It's distributed. That's the key word there, right?
Yeah.
Because we are juggling two specific types of energy.
Correct. We are looking at two main variables. First, there is altitude. In physics terms, this is your potential energy. The higher you are, the more potential energy you have stored up against gravity.
I really like the money in the bank analogy for this. Altitude is your savings account.
Yes.
It's energy you have stored up securely that you can cash in later if you need to.
That is a perfect way to view it. Then the second variable is your airspeed. This is kinetic energy, the energy of motion.
So if altitude is the savings account, airspeed is what, the cash in your wallet?
Exactly. It's liquid assets. It is immediate and ready to spend. Now, here is where the source material directly challenges the traditional flight training dogma.
Okay.
A lot of student pilots view altitude and airspeed as completely separate problems. They look at the altimeter and say, oh, I need to fix that.
Right.
Then they look at the airspeed indicator and say, oh, wait, now I need to fix that.
It's totally whack-a-mole. You fix the altitude, and suddenly your airspeed is off. You fix the airspeed, and now you're drifting off your altitude. It feels like the airplane is pranking you.
And that happens because they're treating them as isolated systems. But the energy-centered approach argues that they are inherently coupled. You cannot change one without affecting the total energy balance or requiring a trade from the other.
So instead of asking, what controls my altitude, the pilot really needs to ask a different question.
They should be asking two very specific questions. What controls my total energy, and what controls the distribution of that energy?
That's a subtle shift, but I can see how it completely changes the decision-making process. Like, if I'm low and slow on approach, I don't just have an altitude problem or an airspeed problem. I have a total energy bankruptcy.
You are in a massive deficit, yes, and you need to deposit funds immediately.
So let's talk about how we actually make those deposits. Let's look at the controls through this new energy lens. We'll start with the throttle. In this framework from the source, what is the throttle's actual job description?
The throttle is the total energy controller. Its primary role is to regulate the rate of change in total mechanical energy.
Total energy controller. That sounds pretty definitive. It's the main supply line.
Think of it in terms of the basic equation provided in the analysis. The change in total energy is a function of thrust minus drag, T minus D.
I want to unpack that a little bit because drag is a word pilots throw around constantly. In this specific equation, drag is essentially the bill we have to pay, right?
Exactly right. Drag is the force that is always trying to steal energy from the airplane and dissipate it out into the atmosphere. Drag mostly varies long-term with your airspeed and your configuration.
Like having flaps down or the gear down.
Yes, or flying at a high angle of attack.
Yeah.
All of those things increase the baseline cost of flying.
And thrust is our income.
Yes, thrust is the immediate variable you, the pilot, change to counter that cost. So look at the math of it. If you push the throttle forward, you are increasing thrust. If thrust becomes greater than drag, so if T minus D is a positive number, the total mechanical energy of the aircraft increases.
So you're pouring fresh energy into the system. The overall net work of the airplane is going up.
Correct. And conversely, if you pull the throttle back and thrust becomes less than drag, meaning T minus D is negative, the total mechanical energy decreases. The airplane is actively losing energy to the atmosphere.
And what if thrust perfectly equals drag?
Then the total energy remains constant. You're in a state of equilibrium. You aren't gaining energy and you aren't losing it.
This is a really important distinction for anyone listening who's grinding through their PPL training right now. The throttle isn't just the go fast lever or the go up lever. It's the faucet. It decides if the total amount of stuff we have to work with is going up or going down.
It completely explains why you can't just pitch for altitude if you don't have the energy to support it. If you're in a situation where you need more total energy, say you want to climb but also maintain your speed, no amount of pulling back on the yoke is going to help you if you don't add power. You cannot spend money you don't have. You have to open the faucet.
Which naturally brings us to the other half of the cockpit equation, the elevator. If the throttle is the supply faucet, what is the elevator? Because I think most of us instinctively feel like pulling back on the yoke creates lift. It feels like we are physically making the plane go up.
It definitely feels that way, but physics says that's an illusion. In this framework, the elevator is defined as the energy exchanger, or as the source material specifically calls it, the distribution controller.
Distribution controller. It sounds like a warehouse logistics manager.
In a way it is. The elevator's job isn't to create energy. It literally cannot create energy. Its only job is to allocate the total energy provided by the engine between your vertical flight path, your altitude, and your airspeed.
So it just decides where the existing energy goes.
Exactly. By adjusting your pitch attitude, you are telling the airplane how to spend its current energy budget.
Okay, walk me through the actual physics of that pulling back sensation then.
Sure. If your throttle setting is constant, meaning your total energy input is fixed and you pull back on the stick, you are trading airspeed for altitude. You are taking kinetic energy and converting it into potential energy.
But I haven't added any new energy to the system.
No, you have just shifted it from the speed column over to the altitude column. And the exact reverse is true. If you push the nose down, you are trading altitude for airspeed. You are cashing in that potential energy to buy kinetic energy.
So the elevator really cannot give you a free lunch.
Never. The elevator can only trade. If the engine is producing a set amount of energy and you pull back to climb, you will lose speed. It is a mathematical certainty. You were simply deciding the distribution.
This really clarifies why that whole pitch versus power debate is so confusing for students. It's not that one controls one thing and one controls the other. It's that they're doing completely different jobs regarding the overall energy state.
Yes. And to really help student pilots visualize this, the source material uses a truly fantastic analogy. They call it the reservoir analogy.
Oh, yeah. I spent a lot of time looking at Figure 4.3 in the source notes. This is the absolute centerpiece for visualizing the system. I want to paint this picture clearly for the listeners, because if you can see this in your head, suddenly everything else clicks.
Let's build it for them. Imagine two large tanks, or reservoirs, sitting side by side. One tank is labeled altitude. The fluid level in there represents your height above the ground. The other tank is labeled airspeed.
Okay, I've got 2 tanks, altitude and airspeed, and they contain this sort of energy fluid.
Now, these tanks are connected at the bottom by a large pipe, and there's a valve right in the middle of that connecting pipe. Liquid can flow back and forth between the altitude tank and the airspeed tank freely, depending on how you set that middle valve.
And that connecting valve between them, that's the elevator.
Exactly. The elevator controls the flow between the tanks. It regulates the flow into and out of the altitude and airspeed tanks. But there is also a main supply pipe feeding into this whole system from the top. That main supply pipe has a valve too. That main valve is your throttle.
Okay, I'm with you. The throttle controls the main supply valve, regulating the net flow into the system.
Right. It determines if the total liquid in both tanks combined is rising or falling. It's that T minus D equation again. If you open that throttle, valve make thrust greater than drag liquid pours into the system.
But which tank does it go into? Which tank rises?
That completely depends on the second valve, the valves between the 2 reservoirs, the elevator.
I see. So the throttle dumps the liquid in from the top, but the elevator decides which tank gets filled by that new liquid.
Or drained, yes. Let's look at a practical scenario. We'll call it scenario A. You jam the throttle forward for takeoff. Thrust is now much greater than drag. The throttle valve is wide open. Liquid is rushing into the system.
We are gaining energy rapidly.
Yes. Now, as the pilot, you use the elevator valve, the yoke, to decide where that new liquid goes. If you hold the nose level, all that new liquid goes into the airspeed tank. You accelerate down the runway. If you pull back, you channel that flow into the altitude tank. You climb.
But because the throttle is wide open and the flow coming in is so strong, I can potentially do both, right?
Yes. If the flow is strong enough, you could fill both tanks simultaneously. You can climb and accelerate at the same time. That is what we call a high energy state.
Now, let's make it a little harder. What about scenario B? Let's say we are just cruising straight and level. Thrust perfectly equals drag.
Okay, so in this case, the main supply is completely balanced. There's no net increase in liquid entering the overall system. The total amount of energy is constant.
But I can still move the elevator.
You can. And this is where the trade-off becomes painfully obvious. If you open the valve to fill the altitude tank by pulling back on the yoke, where does that liquid have to come from?
It can't come from the main supply pipe because that's fixed at equilibrium. It has to be drained from the airspeed tank.
Exactly. You drain the airspeed tank to fill the altitude tank. This is a zoom climb. You go up, but you slow down. The total volume of liquid hasn't changed at all. You've just sloshed it from one side to the other.
And if I push the nose down?
You drain the altitude tank to fill the airspeed tank. You dive. You lose height, but you gain speed.
This visual is just so much better than memorizing rote inputs. It makes you realize that the elevator is just a gatekeeper. It doesn't own the actual supply.
It creates a robust mental model that works for literally every phase of flight. Think about that short final scenario you mentioned at the very start of the show, getting low and slow.
Right. The absolute danger zone.
Mm-hmm.
In our reservoir model, getting low and slow means both tanks are running nearly empty.
Exactly. The altitude tank is critically low. The airspeed tank is critically low. You are in a depleted energy state. Now, what happens if you just pull back on the yoke?
You are trying to open the valve to fill the altitude tank, but the airspeed tank is already empty. There's nothing to draw from.
You try to draw from an empty reservoir. The system completely fails. You stall. And because you have no altitude left, no potential energy to convert back into speed, you have absolutely no way to recover.
That is terrifyingly clear. And it explains perfectly why the flight instructor yells, "Power!" You need to open the supply valve, you need liquid in the system, and you need it right now.
Precisely. You cannot distribute what you do not have.
So how do we take this reservoir analogy and apply it to actual day-to-day flying? Because obviously we don't have plumbing valves in the cockpit. We have a yoke and a throttle quadrant. And usually my hands are busy doing 5 other things.
It all comes down to synthesis, coordinating the controls. The source material emphasizes repeatedly that altitude and airspeed are mechanically coupled. You cannot effectively control the airplane if you treat them as separate, isolated tasks.
Which explains why my flight instructor is always yelling at me to fly with both hands.
It isn't just to keep you busy. To be an effective pilot, you must coordinate both devices to manage the total energy state.
So walk us through the logic of that. I'm in the plane. I want to change what I'm doing. Say I want to transition from a cruise into a climb. what is the thought process using this energy method?
First, you establish the profile you want. You ask yourself, do I have an energy deficit or a surplus for what I want to do? If I want to climb at a specific speed, that requires more total energy than level flight at that same speed.
Because I need to lift the weight of the airplane against gravity. That costs energy. So step one is the throttle.
Yes, the throttle sets the thrust to match the total energy demanded by your desired flight path. You set the supply to meet the demand. You open the faucet.
And step two.
The elevator sets the pitch to maintain the distribution demanded. You use the yoke to ensure that the new energy actually manifests as a climb and not just speeding up in level flight.
It's a synchronized 1-2 punch.
Think of it this way. You use the throttle to satisfy the energy deficit or surplus. You use the elevator to ensure that energy manifests as the correct combination of speed and height.
This makes so much sense when I think about making basic corrections too.
How so?
Well, if you're slightly low on altitude but your airspeed is perfect, you can't just pitch up. If you do, you'll fix the altitude but ruin the airspeed.
Right, you drain the airspeed tank.
Exactly. You need both hands. A little pinch of power to add total energy and a slight pitch up to direct that new energy purely into the altitude tank.
It's pure resource management. That's really what flying is. We are managing a budget of potential and kinetic energy against the constant tax of drag.
It really is. It removes all the guesswork. It's not magic, it's just physics. And when you fly this way, it is so much smoother. You aren't constantly reacting to the airplane. You are putting the airplane in the exact energy state you want it to be in.
It certainly makes for smoother, much more predictable flying.
So let's recap the core definitions before we wrap this up. We've completely redefined our controls for everyone listening.
Yes. The throttle is the total energy controller. It manages the equation of T minus D. It fills the tanks.
And the elevator is the energy distribution controller. It manages the trade-off between altitude and airspeed. It balances the tanks.
And remember the golden rule. Neither works in isolation. They are managing a single, inherently coupled system.
For the student pilots listening, next time you are up there, really try to visualize those reservoirs. Ask yourself, are my tanks filling up, or am I just draining one to fill the other? Understanding this balance equation removes the mystery from your maneuvers.
It might just save you a lot of headache and keep your instructor happy.
Now, before we go, there's one last thing from the source material that I found really provocative. Something for the listeners to chew on.
Let's hear it.
It's about that zero change state we talked about earlier.
Ah, yes. When thrust perfectly equals drag, T minus D is 0.
Right. We said that when T minus D equals 0, total energy is constant. But that implies a hard limit on what the airplane can do. And it made me think about the ultimate worst-case scenario.
An engine failure.
Exactly. That is the ultimate test of energy management. Consider an engine failure. Suddenly, your thrust is 0. But your drag is still very much there.
In fact, if the prop is windmilling, your drag might actually be much higher than normal.
So the equation T minus D becomes 0 minus a big number. It's a massive negative.
You are now in a state of rapid, unavoidable total energy loss. The throttle valve isn't just shut off. The drain at the bottom of the system has been blown wide open.
And you have a finite, fixed amount of liquid left in your tanks, your altitude and your airspeed at the exact moment the engine quits. That is all you have to work with until you reach the ground.
Exactly. You cannot create any more energy. You can only spend what you currently have.
So every single maneuver you make, every turn, every pitch change is just managing that rapidly dwindling budget.
And this is the thought we really want to leave you with today. In that steady state of a glide, your ability to maneuver is purely limited to how much speed you are willing to trade for altitude, or altitude for speed, before you run out of one reservoir entirely.
That is chilling, but also incredibly clarifying.
If you truly understand this limit, that you cannot create energy, only spend it, how does that fundamentally change the way you approach emergency procedures? It's not just about visually hitting a spot on the ground anymore.
It's about arriving at that spot before your energy budget hits absolute 0.
Right. If you try to stretch a glide by just pulling back on the yoke, you aren't saving energy. You are just draining your airspeed tank, moving closer to a stall, and the ground is still coming up at the exact same rate.
You just can't cheat the physics.
You cannot. The math always wins.
That is a sobering but incredibly useful way to think about it. Manage your energy, folks. It's the only thing keeping you up there.
Thanks for listening to this deep dive. Fly safe out there.
That's it for this episode. Keep your wings level, your brain sharp, and catch you next time in the pattern. Thanks for riding with Propeller Breeze.